Okay, so yesterday we went over the indefinite integral and integration by substitution. Today we're going to be talking about the definite integral and U-substitution. Okay, so now that we've seen U-substitution in the indefinite integral, let's see how it works with the definite integral. Okay, so just like we do the indefinite integral, we've got to pick what u is going to be. Okay, so in this you could use either, okay, but some are going to be easier than others. So I'm picking u to be tangent x. So this is my u. And you can see right here that this is du. Okay, so nothing's going to change as far as our u substitution goes. Okay, so here we go. First step, substitute in. There's one problem though. Okay, these limits don't match because these limits right here, pi over 4 and 0, those are the limits for your x values. Okay, so as soon as I put pi over 4 and 0 here, this whole thing became wrong. Okay, because these are not u values. So I have to first rewrite the integral without my limits. Okay, this is correct. Then I'm going to do my antiderivative. Okay, we will substitute the limits back at the end. Okay, so we take the antiderivative. Notice there's no plus c because we're going to put in our limits. So once I replace u back in terms of x right here, then I can put my upper and lower limits and evaluate. Okay, so then I plug in my upper limit, which is pi over 4, and my lower limit, which is 0. Simplify using my trig values from the unit circle. And my answer is 1/2. Okay, so the difference between indefinite integral integration and definite integration is that once I do my u substitution, once I figure out my u substitution here, when I plug in my u's, I can't put my limits in there. Once I take the antiderivative and I plug u back in, then I can use my limits. Okay, so be careful there. This is what we call a linkage error, which means when we're writing equations like this has to be equal to this, and it's not. These two are not equivalent, okay, because you're using these limits. So be very, very careful when we're doing this. Now, this way usually is more work than finding new limits. Okay, so I'm going to show you the exact same example, okay, but we're going to do it a little bit differently. Okay, so I'm still going to do the exact same thing I did before, where I'm going to pick my u as tangent and my du is secant squared x. Okay, but now we're going to find new limits. Okay, we're going to use that equation u equals tangent x, and we're going to find our new limits. So this is going to become the equation that we're going to use to find limits in terms of u. Because remember, these right here, this is x1, this is x2. Okay? So what we're going to do is we're actually going to find what u1 is and what u2 is. Okay? So u1 is what I get when I plug in x1. So I plug x1 into u. So I use this equation right here. Tangent 0 is 0. So my lower limit is 0. And then I use this x2 to find my upper limit. Okay, so these are my new limits from 0 to 1. So now these are actually u values. So when I do my integration, I can actually do my integration in terms of u. And I can plug in 0, 1 because this is u1 and this is u2. These are u values. Okay, which makes it a little bit easier because now when I do this, very easily I get 1/2. Because it's going to be, you plug in 1, you get 1/2 minus 0, which is a 1/2. So basically we've done kind of the same thing. The difference is I've broken it up. Okay, so notice I didn't have to plug back in tangent. Okay, I didn't have to plug in tangent and then use pi over 4 and 0. Okay, so it does tend to be a little bit easier doing it this way. Okay, all right, so let's do another example. All right, this one here, this is another example where actually creating new limits would make it easier on my life. Okay, so we've done a problem like this already. So we're doing U-substitution. I can see that I have the derivative 3x squared, which is the derivative of x cubed, which means my u is x cubed plus 1. My du is 3x squared dx. Okay, which means I'm going to use this equation right here to find my new limits. So I'm going to plug in -1, and when I plug in -1, I get 0. And then when I plug in +1, I get 2. And then I rewrite this in terms of u. So remember, this right here and this right here, that's du. And this right here is u. So this is u to the 1/2, and this right here, that's du. Okay? And I've put in my new limits. So instead of -1 to 1, I'm doing it from 0 to 2. Going to then integrate, which means I add 1 to the power, divide by the new power, so I get 2/3 u to the 3/2. Then we're going to plug in 2, and we're going to plug in 0, and we get 4√2 over 3. Okay, so you can see that this is much, much simpler than at the end, if I'd done it the other way, having to plug x cubed plus 1 in there and do it. So you end up doing almost all the same steps. The difference is that you're splitting up the algebra, and that's when we tend to make mistakes in calculus. Usually we don't make mistakes, it's in the calculus itself, it's usually the algebra. Okay? Now again, I'm going to do this same example, but I'm going to do it with the other method. Okay? So those of you guys that want to do it with dx, getting it all by itself, it would look like this. Basically the same thing. U is x cubed, du is 3x squared dx. You get dx by itself. When you substitute, you're going to get this. 3x squared, square root of u, plus 1 over 3x squared du. And again, the thing I do not like about this is that we have our integral here in terms of x's and u's. Eventually they divide out, which leaves us with basically where we ended up before. But I just, me personally, I don't like having x's and u's in the same function, because if something happens, then it causes issues. Especially there are going to be times when we actually end up having to solve for x and plug in x anyway. Okay, but basically this is the exact same problem, just showing you the other way of doing the U-substitution, and we get the exact same answer. Okay, all right, so let's do one more. So this one's asking us to find the area from 1 to 5 under this curve. Okay, remember, the integral, the definite integral, does give us area under this curve. So when I'm looking here, I'm seeing, okay, I've got an inside function here, 2x minus 1, so that's probably going to be my u. But the derivative of this is only 2, and I've got this extra x hanging out. So I'm going to say that the u is all of that, the square root of 2x minus 1. And you'll see why in just a second. Okay, so this is a little different. Then my u squared, so I square both sides. Okay, I get u squared equals 2x minus 1, and I'll show you why I did that in a second. And when I take the derivative of u squared equals 2x minus 1, I get 2u du equals 2 dx. Okay? Now, that means that u du equals dx. And you'll see what we're going to do with this in a second. Okay? So this time we didn't pick x just to be, we didn't pick u just to be this inside function. Okay? We picked it to all of this as u. Okay? Now, let's do a little bit of substitution. Again, we're going to find our upper and lower limits, but I'm going to solve for x. Okay? So when I solve for x here, and that's what I did right here, I moved the -1 to the other side, making it +1, and then divided by 2, and I get this x. Because what's going to end up happening is I need to substitute in this x, because all of this is now u. And I got this in terms of u. So this is one of those special integration by substitution problems. And then once I plug in x as this, remember, see this right here, this is the x. And when I would plug in u for this in the bottom, there's that u in the bottom. And then dx is u du. And then we can simplify. Okay? Because u divided by u, right here, this and this are going to divide out. And then what's going to happen is this is at 1/2. I can move it. It's just a constant. Move it out front. So I end up with this integration here. Now notice I still don't have my upper and lower limits yet. So we need to fix that now. So when I find my upper and my lower limits, I need to plug in 1 and 5. So I use this equation right here. So u, when I plug in 1, is going to be the square root of 2 times 1 minus 1, which ends up being 1. And u, when I plug in 5, we're going to get the square root of 10 minus 1, which is 9. The square root of 9 is 3. So those are my new limits, 3 and 1. And then just evaluate. (16/3). Okay, so this one is one of those special cases, and we'll work a couple more of these examples in the next couple of days. Okay, but that's definite integrals by substitution.